Okay, so yeah, let's welcome our guest speaker, Eric Park. Today he's going to talk about electronic thermal and unusual applications to the materials.
Thank you. So the mic is on. Okay, it is really working. Good. I can hear the echo. Great. Okay, so thanks a lot, Yuan, for the really nice introduction. It's always a pleasure coming to MIT. I feel that every time I step on campus, because I was an undergraduate here, I feel like I should be taking a final exam. You know, I walked past 26100 and I took 8022 in there when I was a freshman, and I just sort of froze up a little bit. I was, you know, nervous. But I've never been in this building, so I'm actually less nervous now because I've never been in here, so I have no association between final exams and this building. So this is okay. All right, so I'm not going to read the title. I just want to point out the URL of our website. It's a pretty simple one, but that's where we have our papers, you know, students and anyone else that you want to get in touch with. That's the right place. And I'm very, very fondly going to use this stick, I think, for the rest of the presentation. And if you fall asleep, watch out, because I have a stick. You know, I've been showing this slide actually for about 10 years or so. This is probably the only slide that has stayed with me in some incarnation for the last 10 years or so. It is a picture of an egg cooking on a processor that was done about 2005, 2006. I didn't take it. I found it on the internet somewhere. The point is that electronics have been consuming quite a bit of power for a while. And I did put this together, and this is the power density in CPUs over the last 2-3 decades or so. And also what happened around the same time when this picture was taken was that the power density in CPUs hit kind of a ceiling, about 100 watts per square centimeter. And since then, I think it's safe to say that electronics really have been limited by power and heat, since coincidentally about the time that I received my PhD, which is 2005. I like this picture because it captures that very, very quickly in sort of a nice graphical way. When I worked at Intel, we used to joke that that was an AMD processor, which is true. But then when I was a professor at University of Illinois, my graduate students did one of these outreach activities, and they were able to replicate the experiment with an Intel processor. They made scrambled eggs instead of sunny side up. But it turns out the Intel processors also can cook your breakfast. So that's an important thing to know. On a more serious note, I also want to point out this thing right here, which is that the data center power use in the US has been doubling about every 5 years. I think more recently it flattened a little bit because people have actually been making more energy efficient data centers, and also there was a recession around here somewhere, so there was a little bit less installation. But these are large numbers. I mean, this is 10 gigawatts of power used by data centers. Worldwide, I'm told it's about 30 gigawatts power used by data centers. But about half of that is going in cooling, actually. So it's a fairly low-tech use of lots and lots of power. I don't work with data centers or gigawatts, so I had to look this up. But it turns out a gigawatt is about the power of a nuclear power plant, and the whole country of Argentina uses about 12 gigawatts in terms of electricity. So that's about what the data centers in the US alone are using. So these are obviously very, very large numbers. My group obviously doesn't work on data centers. We're primarily motivated by energy and by electronics, more nanoelectronics, if anything. We work on sort of 3 different areas. They're overlapping. Obviously, the main part of this talk is the computing and some sensing with 2-dimensional materials. We also work on, you know, what do you do with all this heat that's generated by things or exists around us? So this is more of the energy harvesting part of the work that we do. And then we're also interested in some of the fundamentals as well as practical aspects of data storage. So we've looked at you know, data storage using phase change materials and resistive change materials. There's some interesting thermal problems in there as well, which we're obviously interested in solving or optimizing or learning about the fundamentals. So primarily my talk will be focused here, but you will see aspects of the other parts of our group work in there as well. So this is sort of my version of a slide which I took from Professor Subhashish Mitra, and this is actually, part of this is really the PhD work of Max Schulacher, who I know many of you know. But the way I guess I think of this sort of in a simplified way is that today computing and memory are typically separated, right? And so that doesn't mean that my computer froze. This is actually something I stole from the internet again to illustrate that basically to compute the logic functions have to wait for memory data to show up, right? So the logic is very fast, but this data bus right here is typically pretty slow, right? So a lot of energy is spent waiting for data to come from memory, and of course the memory itself can actually use up quite a bit of energy as well, especially if it's not non-volatile, if it's volatile type memory like DRAM. And so what Professor Mitra and others have proposed several years ago is that in the future, these things really have to be 3D integrated to the point where you have compute, memory, sort of in what sometimes the popular press calls these the skyscraper CPUs, right? And of course, it's a very, very simplified image. But Professor Mitra and friends have basically calculated that these things could be about 1,000 times more energy efficient than the sort of planar architectures where things are disconnected because of the interconnects are essentially very, very long there. And here the interconnects are very, very short. And so, I know this is not strictly Moore's law, but a lot of people are saying Moore's law is dead or dying. Moore's law, of course, refers to cost per transistor and so on. But in a way, I think what I like to tell people, it's not necessarily dead or dying. It's really things are just going 3D in a way. So these, of course, this is part of the motivation for some of the things that we do. This is a picture which I took directly, again, from the same paper by Mitra and friends. And this is a bit of a more detailed view of what something that's heterogeneously integrated would look like. And again, I just want to point out that, speaking of 2D materials, which I will in a few minutes, the way I think of what's driving us is that 3D is really driving a lot of the 2D work at Stanford. I'm saying much of it because some of it is driven by fundamentals, some of it is just driven by curiosity and so on, obviously. But I'm circling here parts of the system where 2D materials or 1D materials would basically find a place to be, including in thermal solutions. Because of course, if you have something with such high power density, you really need to take care of the thermal problems, and that's what all the orange parts are in this cartoon. So it's a 3D integration of logic, memory, sensors, thermal management, of course, and always keep in mind energy efficiency opportunities. Now, I also have a lot of friends who work in memory, people at Micron, people at Intel, and they like to point out that they invented 3D, really, or at least they pioneered it, right? And so if you talk to memory people, they've been doing 32 layers, 64 layer, and now I think they're working on 96 layer flash for almost a decade, some of these multi-layered memories. But then, sometimes I joke with the Professor Suman Datta, who's a friend at Notre Dame, that actually the real estate people have done 3D even longer time ago. And so 3D is new, but it's also not new, obviously, a three-dimensional integration of stuff. OK, so really just speaking of 2D materials, I know many of you are familiar with them, but this is maybe my little take on them. Graphene is probably the most famous one. That's the one that got the Nobel Prize in 2010 for the people who isolated a monolayer and measured it for the first time. That's a semi-metal, so it'll figure in part of the talk, but not very prominently. Boron nitride is an insulator, again, part of the talk, a little bit difficult to grow. So most of the electronics efforts, for us at least, are in these semiconductors. The monolayer semiconductor specifically, things like molybdenum disulfide, these are 3 atoms thick. But a single layer is 3 atoms thick, whereas here a single layer is 1 atom thick. What we like about these things are the fact that in plane they're bound by covalent bonds, but out of plane they're actually stuck with really, really weak van der Waals bonds. And that's what really enables this heterogeneous integration aspect, which I mentioned earlier, right? You can do heterogeneous integration without lattice matching. Whereas, of course, I'm sure if you're familiar with 3.5s, for example, a lot of this works on 3.5 materials are doing heterogeneous integration by very careful lattice matching. Otherwise, you end up with a lot of defects and so on. But here we can do basically van der Waals growth onto all kinds of random substrates. And it turns out some of this is actually possible at low temperature or lowish temperatures. And we'll see in a moment what I mean by those. Obviously, transferring the layers is done at room temperature, but even the growths can be reduced in temperature. Sometimes I get asked, 2D or not 2D. Sort of that's the question. And so I often run into problems where people are working on fairly thick materials and they call it 2D. And I scratch my head and I go, to me, a 2D material is ultimately something that allows electron motion in 2 dimensions, but really restricts it in the 3rd dimension, right? And so if you look at 2-dimensional electron gases, they look something like that in a quantum well. Physicists have very good definitions for that. And the usual definition is that the spacing between the energy levels that appear in quantum wells is significantly greater than kT. So of course, electrons will basically be confined in one of these energy levels, at most 2, and of course, they cannot move out of plane. So by that definition, actually, if you look at 2D materials, probably anything more than 5 layers is probably kind of a 3D material, just an anisotropic 3D material, as we'll see in a moment. The other thing I want to point out is that the 2D-ness of something probably depends on temperature. Actually, not probably, definitely depends on temperature. And a material could be 2D for electrons, but 3D for phonons. This definition is a little bit in between quotes, but it's there nevertheless, because I think it's interesting to point out. For most of this talk, I really will be referring to single-layer materials. Single-layer graphene, single-layer MOS2, which are really, really truly 2D. There's no doubt about that. On occasion, you'll see a couple of multi-layer materials, but for very specific purposes. So we tend to like the monolayers because they're sort of at the limit of what you can really do with these materials. I think it's nice to show the band structure and then the phonon dispersion of these materials. Graphene, of course, has this beautiful and very well-known sort of V-shaped band structure with very, very high Fermi velocity. This is 10 to the 8th centimeters per second, which is really fast. I mean, that's about a factor of 100 higher than saturation velocity in a lot of materials. But of course, there's no band gap, as you see over there, so that's a bit of a problem. The 2D materials, which are semiconducting, have also a hexagonal Brillouin zone, and they have some funny band structure, which sometimes I think is not necessarily pointed out, but I really wanted to point it out here. In bulk, they tend to be indirect band gap. In monolayer, they tend to be direct band gap. And you can see that these conduction band values are actually dancing around, depending if you go to bulk, monolayer, or if you apply tensile strain for that matter. You can actually break the symmetry again, change the values around, increase mobilities, change the value separations, and so on. The direct band gap of this material, of MOS2 in this case, is about 2 point some electron volts. You might hear the number 1.8 thrown around a lot. That's actually the optical gap of the material. There's very strong excitons in this material. So when you do a photoluminescence measurement, you get 1.8, 1.9. But the true electronic direct band gap is actually larger. And it's also a function of the dielectric environment, it turns out. I wrote approximately 2.2, but it's actually could be 2.3, 2 point something. Strain is very interesting, and I'm actually very interested in the ongoing work looking at strain effects, because they really haven't been studied as much as I think they should be. If I'm going to show you the electron dispersion, I probably should show you the phonon dispersion of these materials as well. It's a bit of a messy plot. It's for multiple materials, but I think the take-home message here is that it's a very anisotropic phonon dispersion. And this has to do with the in-plane covalent bonds versus the out-of-plane van der Waals bonds. If you look in-plane, the phonon velocities are actually pretty good. Heat conduction is quite excellent, in fact. Cross-plane, the heat conduction is actually quite lousy. You can actually see it directly from the phonon group velocities. And so we will be talking about that a little bit later in the talk and how we can leverage that both for good and for evil or bad. Let's hope we don't do anything evil. When I gave this talk, or versions of this talk, maybe 5 years ago, especially to industry colleagues, the question was always, well, isn't that sort of that really funny field where you just work with Scotch tape and you get little pieces and it's nothing really useful, right? And so that's true, right? This started with Scotch tape, working, people just exfoliating from bulk crystals and getting maybe random 10 micron scale pieces. But I'd like to tell my students, or I like to joke in my group, that we've essentially canceled our Scotch tape budget. We no longer buy Scotch tape. We try to grow everything these days, right? So everything is grown. If it's not grown wafer scale, at least it's grown some sort of a chip scale or relatively large area scale, either by chemical vapor deposition or by chemical vapor transport. The CVD is done in my lab. The CVT is done in Ian Fisher's lab in the physics department. And so he prepares some of these more unusual 2D materials for us, which do show up as multi-layers, and then we have to separate the layers. But some of the other things that we prepare are by CVD. This is what our growth lab looks like. This was actually something we set up when I moved to Stanford 5 years ago. It's all fully operational right now. This is the selenides growth, and this is the boron nitride growth down there. I'm not showing it, but we also have a 4-inch growth system for graphene, and we have a separate 2-inch system for growing for the sulfides, the molybdisulfide, basically. And I do want to highlight that a lot of this work is actually based on Jing Kong's work from here at MIT. So we've learned a lot from her papers. A lot of the tricks that we employ are directly based on her work, and we're very, very grateful for her friendship and her help, actually, you know, over email, over phone sometimes, with setting some of these things up. Another thing that I think people sometimes don't state, but I want to come out and tell you, especially if you work in this field, you're going to nod smilingly. If you don't work in this field, you may have not seen this before. Some of these materials are not really stable. And you know, if you've worked with graphene or carbon nanotubes, you go, okay, those are actually pretty good. Moly disulfide, not too bad. But my student Michael Mleczko actually put together this plot of you know, this is sort of the most stable, and these are sort of the least stable. So if you go heavier chalcogens or the heavier metals, these things get more reactive. And then, you know, nobody in my group wants to touch black phosphorus because that stuff just burns upon, you know, contact almost. So there's not much black phosphorus in this work, actually. We tend to work with the more stable chalcogenides, basically. And this, of course, is just kind of a very qualitative thing. But it is something worth pointing out. Our solution to this, by the way, is to cap them. So when we work with materials which are a little bit more unstable, what we do is we work with them in a glove box, and then we have a PMMA coater directly in there. And the glove box is also directly connected to a ALD system, or we can coat them with aluminum oxide. So we either coat them with PMMA, and then we can do lithography later, or better yet, for devices, we try to coat them directly with aluminum oxide, which is part of Michael Mleczko's work, actually. And that will basically keep them alive for much, much longer, the aluminum oxide coating, and lack of air exposure. Okay, so this is kind of how I broke up the rest of the talk. I will say a few things about graphene. Graphene's probably the 2D material we've taken closer to simple systems. The semiconducting and insulating materials are obviously more sort of a device level, and you'll see some of the thermal and maybe a little bit wackier or unusual or fundamental sort of questions that we're trying to answer. So, of course, we're primarily electrical engineers in my group, so you can imagine that transistors are a big driver for what we do, right? To sort of paraphrase my colleague Philip Wong, Philip likes to say that you know, 20th century transistors are really carved out of a rock, right? Silicon's basically a rock, and this is what Intel's carvings, you know, look like from that rock. This is a cross-section of the so-called 14 nanometer FinFET technology from Intel, which is inside my laptop right now. I say so-called, and I put it between quotes, because notice there's no 14 nanometer dimension in there. 14 nanometer doesn't really mean anything. It just means it's somehow better than 22 nanometers. But it's, you know, just like my Google Pixel, you know, 2 phone is better than the Google Pixel 1 or something like that. But, you know, it is small. It's impressively small, and you can see every atom in here, which just blows my mind. I think this is very, very cool. But, you know, if you're an electron that's rattling around this fin, actually the transport is out of plane, you're going to be scattering on these interfaces. You can imagine that. And this is my, obviously, very crude attempt of showing electron scattering. For silicon on insulator film, there's work going back, you know, at least 15 years. To Ken Uchida and Shinichi Takagi's work, looking at essentially surface roughness, limited mobility in very, very thin, down to 2 nanometer silicon films. So this has been known as a limiter for very thin silicon for a while. And it is a problem in FinFETs as well. So in fact, if you look at mobility as a function of thickness for these materials, this is experimental data that basically shows that below about 3 nanometers in thickness, whether it's a film or a fin, the mobility of silicon is actually, you know, tanks. I mean, it really grows from, you know, hundreds in doped inversion layers down to tens, down to, you know, very, very small values, and pretty much all entirely due to surface scattering and remote phonon scattering to some degree. So that's where, you know, what Philip and I call 21st century atomically thin materials could fit in, at least transport-wise. Of course, there's carbon nanotubes and 2D materials, both fit in the same place. Graphene carbon nanotubes have good mobility. That is a function of thickness, function of diameter, but it's good in general. And then some of these materials have larger band gaps, but they also have pretty decent mobilities for the thickness regime that is very, very difficult to touch with bulk materials, certainly with bulk silicon. The band gaps, by the way, also change quite a bit when you take these materials and you confine them into quantum wells. And again, if you need like a sort of a decent band gap of, you know, 1 to 2 eV at these thicknesses, then you're probably in pretty good shape working with some of these materials. And the reason this happens is because these materials don't have dangling bonds. They don't have rough surfaces, essentially. They still suffer from remote phonon scattering if they're embedded in dielectrics. So that stuff is not going to go away. And of course, we need to to worry about that and screening and so on. Okay. So when we started working on graphene, which was, gosh, about 10 years ago, there are obviously a lot of physicists and chemists in the field. But we're interested in transport problems as well. And what the problems that hadn't been tested yet were mostly at room temperature and at high fields. And so one of the first things that we did is we tried to actually measure transport in this regime, specifically in this case, focusing on the saturation velocity in this material. So saturation velocity, you probably know from your basic semiconductor course, is the velocity, the average velocity of drift carriers as you go to high fields. In silicon, it's about 10 to the power 7 centimeters per second. In germanium, is about a little bit less than that. Varies a little bit on doping and temperature, obviously, but in general, they're pretty well known. In graphene, the numbers are higher, maybe a factor of 2 to 3 times higher. But the surprise at the time was that they're actually a function of the carrier density. And that has to do with the funny band structure of graphene. In graphene, you have, remember, those Dirac cones that are so elegant. But the fact that you have those Dirac cones is also increasing your density of states for scattering when you go up to higher fields and higher energies. And so that actually leads to this 1 over square root of n dependence that you basically see over here. It's actually captured in that term. This term is actually not really dominant, but that's the term right there. And so you see that from the model directly. You also see that if you're worried about scattering with a substrate, you're actually probably scattering with the SiO2 phonons. And this goes back to that comment I made just a minute ago about remote phonon scattering that you see in these ultra-thin materials. That really is still there, unless you suspend your material. So that's basically what we were doing there. We have a habit of doing modeling work as well. In fact, most of my PhD work was on modeling. So there are obviously a lot of modeling sort of questions or answers really provided throughout this talk with some focus on compact models. But these days, we're also doing molecular dynamics for certain problems. So we really span the range. More recently, we actually came back to re-examine this high field transport problem. But this time, we work with Professor David Goldhaber-Gordon. And David is in physics at Stanford, and he really likes to work on very, very clean systems. He said, forget SiO2, that's a bad substrate. Let's use boron nitride. Boron nitride is an ultra-flat 2D layered insulator with large phonon energies, it turns out. And so the mobilities that we can get in graphene on boron nitride are approaching 100,000 at room temperature. So these are incredible mobilities. These are incredibly good samples. Very difficult to make. These are made with Scotch tape, by the way, sort of one at a time. Very, very difficult. I do want to highlight ultimately this is an expected result. We got very large saturation velocities. I think it's the largest one recorded in a solid at room temperature, about 6 times 10 to the 7 centimeters per second. And the numbers are about 50% greater than what we were getting 10 years ago in SiO2. And this is the difference between the remote phonon scattering with SiO2 versus the boron nitride. The only thing, so that was probably expected. It's nice to know the numbers, but it was probably expected. What I do want to point out is that the unusual part of this component was that this work was largely done by a high school student named Megan Yamoa, who is a sophomore at MIT right now. So she worked with us when she was 16 and 17, I want to say junior, senior in high school, and she's now in the physics department here doing other things. She sort of moved on, but something cooler probably. But very, very nice work. Okay, those are sort of just 2 examples, sort of basic transport examples that we've done. We've also looked at more system-y things. With graphene, of course, because it's a more mature technology, at least for us. And so I mentioned earlier that we can grow graphene over 4-inch wafers. And obviously we knew that graphene, without having a band gap, it's probably mostly good for interconnects, which we're studying. But it's also good for analog circuits, it turns out. And to achieve some of this work, we got in touch with Professor Naresh Shanbhag, who is a colleague of mine at the University of Illinois. And Naresh and my students and I had a brainstorming session where we basically selected a very, very specific problem to pursue using graphene. In this case, it's a very specific nanofunction. That's what Naresh calls these things. It's a nanofunction that computes the dot product of 2 4 input vectors. So you see the 4 voltages here, and then the 4 voltages, V and phi over there. So a dot product is basically what you think it is. It's just a scalar product of 2 voltage vectors. The devices themselves are actually fairly average. These are not world record graphene devices. Mobilities are probably a few thousand. The channel lengths are a couple of microns. The secret sauce, maybe not the secret sauce, but the breakthrough here was really more of a heterogeneous integration challenge to do this in an academic fab. And also the fact that we are able to focus on a fairly unique function where graphene actually shines compared to silicon because of its higher mobility. So if you do the same thing in silicon, this will actually be slower. And you'll still get the right answer, but it'll be slower. And so graphene is really better here because of the higher mobility. OK. So that was the part on graphene, just selecting a few things from the graphene work. I want to say a few words about the growth of the other 2D materials. This is, like I said earlier, this is inspired by a lot of work done by Jing Kong here at MIT. Our version of this is a little bit different. Recently, we've been able to grow these things down to 580 Celsius, which is not bad for at least memory integration. For logic backend, you probably need to be below 450 Celsius, so doing layer transfers is still probably a better way to do it, and industry doesn't like that. But for memory integration, 580 Celsius, people are actually starting to talk to us. Here's an example of basically this monolayer film grown over a centimeter scale. This is about 1.5 centimeters by 2 centimeters, the obligatory Stanford logo in the middle. But this is, by the way, etched. This is just directly etched into it. So you're seeing the contrast between a monolayer material or 3-atom thick material and no 3-atom thick material. That's actually pretty cool that you can see that with the naked eye. This growth can be replicated on pretty much any substrate that we can stick in the furnace, and it's pretty flat. Silicon oxide, quartz, silicon, aluminum nitride, we've grown on sapphire. Anything that you can stick in the furnace that's flat, it'll grow on, and that's actually pretty good for this kind of van der Waals growth. If you look in the middle of the chip, it looks boring, right? It's boring, good boring. It's basically just a flat monolayer, and that's great. If you look towards the edges of the chip, I'll be honest with you, we actually don't get perfect coverage of the chip. And so you get these sort of 100-micron polycrystalline grains, which are not always touching, right? We can go and do a device on one of these grains, but obviously we prefer to work with the continuous regions in the middle of the chip. Because this work was being done in 2016 during the presidential election cycle, we decided it would be fun to etch a nanoscale Trump and a nanoscale Clinton onto some of these polycrystalline grains. So there you have it, nano Trump and nano Clinton. And later, one of my colleagues pointed out that nanoscale Trump should be tweeting something. So he tweets, "Make MOS2 great again." On a more serious note, you will notice that the nanoscale presidents look like they have acne or chickenpox, right? Their faces are dotted. And so that's actually bilayer MOS2. Our growths are not perfect. Sometimes we get these beautiful monolayer coverage, but sometimes we get a few bilayer regions, right? And when I first saw this, I got really worried. I said, that's a 100% variation in layer thickness. You go from 3 atoms to 6 atoms. That's probably bad for any kind of large-scale integration. We really ought to study that. And so we did, but before I tell you that story, I just want to show that at least where we have monolayers, they actually look pretty good. This is obviously a very small zoomed-in TEM image, but they do look like the way they should. You see the monolayer atoms, they're all there. Of course, if you look in other regions, you'll see defects and grain boundaries. But the stuff is there. It really does work. So going back to this variability question, we saw the monolayer bilayer variation, and I was worried. 2 years ago, around this time, I really was worried. Actually, probably 3 years ago that happened, 2016. But because we have so many of these devices, we basically just made hundreds of these devices. My student Kirby Smith measured all of these things. He tabulated all the mobilities, all the contact resistances, all the doping. He estimated, everything is in the paper. And I'm proud of this work in the sense that I think a lot of people who work on sort of nanoscale devices, a lot of groups will sometimes pick their best device, or maybe they only have 3 devices because they're so damn hard to make. But then they will, obviously publish sort of the best device. And so here, I'm showing you the best devices and the worst one. There's hundreds of devices in here. And I'm saying, look, they all worked, but there is some variation, right? And this is where talking to systems people like Subhashish Mitra or Naresh Shanbhag is actually quite useful, because sometimes they come back to us and they say, that's not bad, don't worry about it, right? We can work around that. But sometimes this is a real problem. So we need to understand what are the sources of variation, both in mobility as well as in contact resistance or threshold voltage or whatever. To make a long story short, it turns out that I was almost needlessly worried in 2016. Maybe I worried too much. It turns out that the variability that we see in these samples is actually significantly lower than you would expect for something like silicon that would, if you were assuming silicon to vary by 100% in thickness. And so we catch a break. The break has to do with the physics, or the chemistry rather, of the material. It turns out that if you have monolayer, bilayer regions, the conduction band offset is only about 55 MeV. We were not the first people to point this out. We found a few papers before us who pointed this out as well. But I think we were the first to point out that in the conduction band, this means that the electrons don't really see these energy sort of barriers, right? Because this is 2 kT. So it's kind of a small scattering potential if you think about it. For holes, it's a different story. If these materials were used like p-type, then obviously we need to restudy their p-type behavior and variability. But at least for now, I can say that for n-type, I sleep better even with the bilayers being there. Although, of course, I would prefer to have mostly monolayers. OK. We have a habit in my group of doing thermal measurements. And in this case, this really was motivated by variability. We said, hey, we can measure the temperature of these devices during operation. But these devices have bilayer regions in them, right? And so we started taking these thermal images using Raman thermometry and scanning thermal microscopy, actually both, of these devices during operation. And what's interesting is, again, even by thermometry, we don't see the bilayer regions. That's good. That means the bilayer regions they're not really hotter or colder than the rest of the channel. So that means that they're almost invisible in a way to electron transport, which again is confirming what I stated earlier. One maybe other take-home message from this work is that when you do these IV measurements, especially if you push these devices to reasonably high fields, these are large devices, by the way. You can sort of see this is an AFM image, but they're like, this is probably a 5-micron device. So we're taking it to obviously pretty high voltage and high fields. But anyway, when you take these IV measurements, we learn that these devices actually get quite hot. And so ever since we've done this, I've realized that actually all the IV data, especially the high field IV data we had taken earlier, probably needs to be maybe slightly reinterpreted, because by the time that you get up to high field, your device is no longer at room temperature. It's actually probably at about 200 Celsius if you started at room temperature, right? If you start at 77 Kelvin, then it's probably at room temperature by the time it heats up. So this is, it's good to know. And if you look at these papers, you can see how to calculate this without doing actually the measurement. You can learn how to calculate this. But there's another question about why is this happening, right? Why is my device not well heat sunk? And there's 2 reasons. One is we're putting it on SiO2. From the days of SOI, people have known that SiO2 obviously is not a very good heat sink, right? So there is a problem, and we probably should not be putting on SiO2, or should be putting it on thinner SiO2. But there's a more fundamental problem. And the more fundamental problem is that there's actually a very weak thermal boundary conductance between this weak van der Waals interface between the MOS2 and the SiO2. Remember I mentioned that the materials stick to things by weak van der Waals bonds. It turns out the weak van der Waals bonds are also bad for heat flow. And so that is something to be a little bit concerned about in heat dissipation or power dissipation, anything based on these things. And so you'll see some ideas that we have with this, but it's something to be aware of. So to recap, van der Waals bonds, great for heterogeneous integration, bad for heat removal. Sort of on a related note, if you have a motivated student and a decent E-beam system, you can take these materials and actually make them into 10 nanometer gate transistors. This, by the way, is a cartoon, obviously. This is the real finished device. What I like about this is it looks like an SOI device, if you're familiar with SOI devices, but it's really made with a 3-atom thick channel, right? So it's kind of like the ultimate SOI device in a certain way. At the time, the saturation current in these devices was about 400 microns per micron, which is reasonable. If you look at SOI papers, they do a little bit better sometimes, but it's done with really much, much thicker silicon, at least 10 times thicker silicon. The devices were not as ballistic as we had hoped, and that has to do partly with the contacts and partly really with the mobility is not quite as good in this material, and the effective mass is a little bit heavier. So those are things to be worked upon, and especially from an engineering point of view, contacts and doping, those are really, really big bottlenecks for us. And so just speaking of contacts, our contribution in the contact, field for these materials is actually fairly simple, but it turns out practical. We basically had access to multiple metals and multiple evaporators at Stanford. And lo and behold, maybe in retrospect this sounds very, very trivial, but we realized that if you actually deposit gold in the cleanest evaporator that you have, the one with the load lock, the one with the really low base pressure, you can actually get much better contacts than if you do it in sort of a more dirty, more run-of-the-mill evaporator. Titanium contacts are actually particularly bad in our experience. We avoid titanium at all costs because it either attacks the sulfur, so it makes tisulfide, or it just oxidizes. In fact, in the poor evaporators, titanium basically gets down and it becomes tioxide. We've seen this by XPS, and other groups have seen it as well. So as much as possible, we use pure gold for our contacts. And then if you're worried about sticking, you still use Ti gold underneath the pads and sort of like farther out. But these leads right here are pure gold, and those are actually the best contacts in our group right now. The contact resistance is below a kilo micron, but this really ought to be about a factor of 10 lower. These are undoped contacts, so doping of course helps, as I'll show in a moment. I also want to say a word about fundamental limits. We're always sort of wondering, we did this measurement, but how is it approaching the fundamental? How much better can we do? So we have simulations for that. It turns out if you have the best ballistic contacts that you can imagine, we should be able to do a heck of a lot better, which is both good news and bad news, right? I mean, the good news is that we have a lot of room at the bottom, to paraphrase Richard Feynman. The bad news is that we have a lot of room at the bottom. We have a lot of work to do, right? So, but that is also good. So we know we can still improve this quite a bit. I mentioned doping. There's two ways we do doping in our group, and we were very, very interested in making stable dopants. It's possible to dope these things with liquid dopants or gel-like dopants, but they're not 3D integration compatible. And so one, simple way to dope these things is to pretty much put aluminum oxide on top of them. And if it's substoichiometric, the aluminum oxide is essentially charge transferring to the MOS2, and it's doping at N-type, and it's a very, very stable capping doping layer. And so by doing this, we've actually achieved record current densities of about 700 micrograms per micron in these devices. And again, keep in mind, this is 700 micrograms per micron through a 3-atom thick transistor. And the contacts have also improved to be about just below half a kilo micron. And actually, if I replot the current density in units of megaamps per square centimeter, this is where we are right now for some of these devices. These numbers are huge, actually, for a 3-atom thick material, about more than 100 megaamps per square centimeter. The electromigration current density of copper is about here, maybe even a little bit lower. So the current densities are actually quite high. But what's limiting this? Why can't we do better? For now, it's still phonon limited. Material phonons, substrate phonons, it's basically heating, right? So we could probably do better than that, even hit a milliamp per micron in a 3-atom thick semiconductor if we can figure out the thermal problem. And actually, my student Connor, who's done this work recently, he actually went and looked at, this used to be the ITRS, now it's called the IRDS, the International Roadmap of Devices and Systems. And we're taking a little bit of liberty with this benchmarking, because obviously this is done at slightly lower voltages than what we're doing, and different threshold voltages too. But we are in the ballpark of the requirements for IRDS kind of devices, future technologies, whatever they are, but with a 3-atom thick transistor. And I do want to point out that the off-state currents for this material are actually 1,000,000 times lower than the benchmarks, simply because we have a very large band gap. Silicon has a one-ish EV band gap. We're operating at a 2 EV band gap, roughly. So you can imagine the off-state currents are actually significantly better than required right now. Okay. That was all about MOS2. I want to say just 1 or 2 words about the selenides. The selenides, we don't have very good devices, so this is really more materials-y. We can grow tungsten selenide these days. And we like the tungsten selenide because it's one of the 2D materials that we can dope both N-type and P-type. MOS2 is very difficult to get P-type. The N-type, of course, is done using aluminum oxide if necessary. P-type is done using moly oxide on top. And this is actually a beautiful crystal of moly oxide grown directly on top of WSE2. This is done with Xiaoling Zheng's group at Stanford. And it's quite a stable doping as well, and it's P-type, and it gives pretty good sort of hole doping for these materials. So this is what we're doing with WSE2 at the moment. These are different selenides. These are hafnium selenide or zirconium selenide. Note for now, these are multi-layers. Everything else I've shown you pretty much is monolayer, but these are multi-layers. And the way we started working with these selenides is actually it's kind of a reverse engineering kind of thing, because my student Michael Mletzko started thinking about, hey, you know, if silicon is great because it has native SiO2, what material will give us native hafnium oxide or zirconium oxide? And it turns out the answer is hafnium selenide and zirconium selenide are such materials. They happen to be 2D materials. And so here you see a TEM of zirconium oxide formed natively on zirconium selenide. And we can actually make real transistors out of these things. They're not very good transistors right now. But it is kind of neat, I think, to have transistors with native high-K dielectrics. And I was pleasantly surprised when the TSMC CTO at the time highlighted this in his IDM plenary, meaning that TSMC reads my papers. So and that's before Philip Wong went to TSMC, in case, for those of you keeping track of Philip's trajectory. Maybe one word about HBN, and this is also inspired by some of Jing Kong's work. In fact, I hired her former student as a postdoc when we started working on this. Most recently, we've been able to grow HBN directly onto carbon nanotubes, so that's kind of cute. This is actually work done with Applied Materials. We're growing directly onto carbon nanotubes. Carbon nanotubes can withstand the growth temperatures. We can also grow multi-layer boron nitride. For memory applications, it turns out, these are defective, so they make decent memory, resistive memory. But we're also interested in boron nitride heat spreaders, as you can imagine, because the thermal conductivity is supposed to be pretty good. So we're in the process of measuring their thermal spreading properties at the moment, since we do quite a few thermal measurements. So I probably just have a few minutes left. And I just want to say a couple of words, maybe 5 slides, about the thermal measurements that we're doing. Again, the take-home message of the thermal measurements is this thermal anisotropy of 2D materials. You don't really get this in 3D. In 2D, you have very large thermal conductivities in plane, but you have pretty lousy thermal conductivities out of plane, cross-plane, because of the weak van der Waals bonds, right? And so, we became interested in what can you do with this, right? How can you tune this? Can you do better or worse than Mother Nature does with these materials? And in this case, in a way, we've done worse than Mother Nature. And the way we've done that is we realized that if we actually do a wacky multi-layer of these materials, in this case, graphene, MOS2, WSE2, we can, again, this is done by hand, so this is not directly grown. They're grown separately, but then layered by hand. What we're doing, deliberately, obviously, is we're actually mixing and matching layers that have very, very different atomic mass and phonon density of states mismatch. And if you do that on top of the weak van der Waals bonds between the materials, you actually get these very, very large interlayer thermal resistances. So the cross-plane thermal conductivity of these artificially stacked materials is actually way, way worse than Mother Nature. In fact, it's worse than air. For a solid material, this is actually pretty bizarre. It's really, really an excellent phonon blocker. That's basically what it is. And it's just relying on simple acoustic sort of propagation, or in this case, acoustic impedance mismatch kind of concepts, where we're just deliberately layering light, heavy atoms. You can actually see that the worst thermal conductance is actually between graphene and WSE2, and that's not a coincidence, because that's the biggest mass mismatch between the materials. Okay. There's actually an application for this, it turns out. Of course, you can block heat. That's great. Maybe it's something to wear in the cold winters. But it turns out in electronics there's an application. An immediate application is in phase change memory. In phase change memory, you really need a really good electrical, a decent electrical conductor, but a lousy thermal conductor to basically thermally insulate a little memory cell or a memory bit, right? And it turns out what's unusual here is that at first we just use graphene as a thermal barrier. And again, graphene, people say, well, graphene's got a good thermal conductivity. What are you doing? But it turns out that out of plane, actually in this direction, graphene by itself really blocks heat flow. And we got 40% current, programming current reduction for this type of memory technology. More recently, this paper actually just came out in APL. So I made sure to update the slide last night. We've been able to do this with MOS2 as a heat blocking layer, just an MOS2 by itself. And it's a sort of another 20% or so reduction of programming current compared to graphene. So it turns out these things are pretty good as thermal insulators, deliberate thermal insulators in a certain way. Another sort of unusual application is this concept of thermal transistors. The concept of sort of actively controlling the flow of heat has been around for a while. But it turns out it's quite difficult, right? You can control electrons very nicely because they're fermions. You have a gate, you can whip around the Fermi level. But phonons are bosons, and you can't move around their Fermi level anymore because there's no Fermi level, right? And so the way to do this is, in this particular case, is to actually work with multi-layer MOS2 and to push lithium atoms between the layers and then to pull it out. Push lithium in, pull it out. Professor Yi Tsui at Stanford is a battery expert, and they're very good at doing these things in real time under a thermal measurement system and so on. And so to make a long story short, here's the thermal conductance cross-plane varying as a function of lithiation and delithiation of this multi-layer stack. Again, this is heat flowing in the cross-plane direction, and what's cool is that this thermal transistor has an on-off ratio of about 10. And if you work with graphene, you know that's a good on-off ratio. And so for a thermal transistor, of course, we'd always want it to be higher. Turns out the higher the better for thermal transistors too. But 10 is actually pretty significant for modulating heat. The only downside here, besides the fact that it's kind of a messy experiment for now, is this is not very fast. It's timescales of minutes. So we need to speed this up somehow. But it does work, so that's kind of neat. OK. My last technical slide is pretty much here. And this is half technical. We do a lot of stuff with thermometry. And actually, we're working with Professor Kim on some of the thermometry of memory. Recently, we've gotten very excited about using scanning thermal microscopy to literally look for hotspots in these memory devices that G1 makes, as well as memory devices we're getting from industry or that we make. And here's one of these. It's like a 50 nanometer hotspot that we can see directly in an RRAM device where that conducting filament was formed. I have another student, Stephanie Bohaichuk, who is mapping the temperature of individual carbon nanotubes. In this case, she's using a carbon nanotube to trigger a nanoscale insulator metal transition in vanadium oxide, partly for physical curiosity and partly because it turns out there's some interesting applications, such as like very small memory selectors that could be enabled by this. Maybe not with VO2, but at niobium oxide, but still this is a way to scale them down. She's also made oscillators out of this because it turns out the metal insulator transition is very unstable. So you can actually go back and forth if you bias it in the right place, the device. OK, so I sometimes attend these NSF workshops on 2D materials and devices. And one of the things that they ask us to do is to say, what is our wish list for research drivers? And this is mine. I group them by growth, metrology, and electrical things that I like to see. I think there's general agreement that growth at lower temperatures would be good. We've gotten down to 580, but 450 would be excellent. Boron nitride really needs to get better. Whether we do it, we're probably not the right group to really improve on boron nitride. But again, I had a nice conversation with Professor Kim about some collaboration that he has to enable that. We're struggling with defect density. I really don't know the defect densities in some of my devices. The nice way to do that would be TEM or STM, but that requires a lot of work. I'd love to have a rapid sort of turnkey, way of determining defect density. So if you have some ideas, please talk to us. And of course, nobody will ever complain if your mobility gets better. The higher the better. Hundreds of thousands, please. Nobody's going to complain if the contact resistance is 0, but the number to really aim for is 100 ohm microns, and for industry purposes specifically. And then this work we've done with doping, I don't know if it's the best way to dope these things, but it's certainly a stable way to dope these things. But we need better control over doping. So I will stop right here. I want to thank the people who have done the work, obviously the people sponsoring the work and the agencies funding it, and I really want to thank you for your attention. I'll happy to take questions. Thank you.
Okay, any questions?
Yes.
How exactly is the saturation velocity?
Yeah, by reading your papers. The saturation velocity was measured by doing careful carrier density measurements, right, and then measuring the current. So ultimately dividing current by carrier density, right? And the carrier density measurements are done, the work with Goldhaber-Gordon was done, they're Hall measurements, so we also have that verification. The work that we had done earlier, they were just very, very careful estimates from gate voltage minus threshold voltage and having very, very stable threshold voltage and essentially just getting it from that.
But when you're applying a voltage across the film, obviously the Fermi level is tilted.
That's right. Yeah, and we're very aware of that. And so there's oh, it's gone. Sorry, I thought I was showing you a different slide, but I lost it. Let's hope it comes back. So you notice that this is a tricky thing, right? You really need constant field across the device, because if you're actually biasing it in the real sort of saturation regime of the transistor, you're going to have pinch off over here, and so you're going to have a very, very different carrier density and velocity profile. So basically, we struggled with that, and we really have to bias them the right way. And in our papers, we sort of state that, look, the carrier density from source to drain, we try to keep it varying no more than about 10%. So we sort of put upper limits on how much we're willing to vary the carrier density. In a way, you can think of this as they are gated in a linear regime, right? Insulator. We have thick insulators by design, in a way. But the thick insulators actually allow us to basically keep the devices always operating in the linear regime, right? But the lateral fields are large. And so we have actually not a huge difference in the carrier density from source to drain. But that's part of the error bars. The error bars are not on here, but they're part of the paper. So actually, that is taken into account within the error bars. Yeah.
Other questions? Okay, so I do have a question for your lithium device. If you look at if you go to the slide.
Yes, I can do that. But yeah.
It's really like analog computing there.
Yes, very good.
This one, so by each point has thermal cycle, right?
Each point is a different thermal conductivity measurement, thermal conductance measurement, as a function of time. Yeah.
As a function of time.
Yeah. And lithiation.
So as time goes by, just lithium content
goes in. Yeah.
Goes in and out.
Yeah, it goes in and out. Yeah.
I see.
Yeah, and we can actually even see that in real time. Like we can do this. It's not on the slide, obviously, but it's in the paper. You can actually see these sort of thermal maps of the device, and you can actually map the lithiation of the device as the lithium kind of moves in. And it's not a super fast process, unfortunately, right? But there are ways to speed it up. But it's just naturally not a very fast process. But we can actually see this in real time. I think there's a movie of that in the supplementary part of the paper.
You can control this.
Yeah.
Some thermal pulse. This is really ideal analog computing curve for the neuromorphic computing.
Okay, all right. We hadn't thought about that. I will tell you what we did think about is that having a something that has a variable thermal resistance could be used for controlling thermal transients. So sometimes, when there's a huge thermal transient affecting your device, or when your device itself turns on and has a big thermal transient, you can basically use a variable resistor to control that, in addition to having thermal capacitance there. So sometimes people will do, control thermal transients simply by having thermal capacitance, but having a variable resistance gives you sort of another knob for tuning thermal transients. And so that was sort of the original application of this, or at least the original thinking, besides the fact that, hey, thermal transistor just sounds kind of cool. And so, sometimes you just kind of want to see what's going to happen. But I think, in my mind, it's controlling thermal transients that probably would be useful for. And there might be something what you suggested, yeah. All right, cool.
Any other questions? Another one, since somebody else is asking. You showed an improvement in mobility when you used native oxide.
Oh, no, actually, those, I can go back to that because it's without getting out of this mode. We didn't quite get that. No, actually, in fact, these devices did not have very good mobility. Nobody's really made very good devices with these materials, it turns out. Maybe Tomas knows better, I'm not sure actually. But as far as I know the literature, nobody has made particularly good transistors with these materials. The currents are not very high. I believe our best estimated mobilities were less than 10 centimeters squared per volt second. I think the cool thing here is that these even worked with native oxides. I'm trying to remember, it is possible that we had some improvement with a native oxide, but I wouldn't necessarily call these mobilities significantly improved. And part of that could be because we don't have very good control of this oxidation process yet. You see there's this zirconium oxide there ate part of the layers, and that's where the inversion layer is. So there's probably some significant, not just remote phonon scattering, but even surface roughness scattering there. And this is really not an optimized process. But I agree with you in the sense that certainly having native oxide should give us better mobility in these materials.
But native oxide is not, to have a native oxide doesn't mean that you necessarily have a transport. No? For example, in gallium nitride, we really hate gallium oxide.
I see.
So we try to avoid it in any way we can, even though it's a native oxide.
I see. How good is that oxide, though, as a high-K dielectric?
It could be okay, but the mobility suffers, and you do have interface density issues
Right,
and
right.
so on. So I think it's also...
But it does come down to the interface states, for sure.
How uniform, so it's not about the native oxide, but how uniform the native oxide is, and the crystalline structure. Do you only have this kind of native oxide, or do you have multiple polytypes?
Polytypes, yeah. I don't know the answer to that question, to be honest. So, I believe we've done this also with aluminum oxide, and I don't think the results were necessarily any better. But these are sort of like tricky materials to work with to begin with, because they're actually quite difficult to process. These were all done in glove boxes, and they're just not that easy to work with. So, it's hard to really answer Professor Antoniadis' question actually in this particular case. And you make a very good point that it's ultimately about the quality of the interface, and There was a, sorry, go ahead.
Have you ever made a CV measurement? If you do CV measurement, you can extract the IPR.
I don't remember if we did CV measurements or not. We may have. I just don't remember.
But I think the idea is still really good. Let's find an oxide that is very stable and
a desirable oxide
a given time.
Right.
Let's look at the semiconductor material that will oxidize.
That might give us that. Right. Yeah, and hopefully we can find one with good mobility, or decent mobility. Yeah, there's some other. Yeah, there was one over there as well. So
yeah. Oh, no, you're
he was first.
Yeah.
I had a question regarding the thermal management. So you were pointing out how mismatching the two materials actually makes it even worse to transport away the heat. Do you have any ideas on how to make it better? Like you said that HBN, for example, has good properties. Could you put that under any tuning material?
Yes, yeah. HBN is the sort of the simple, the obvious answer there. You're absolutely right. HBN has mobility comparable to copper, right? But it's an insulator, so I love it for kind of like back end of the line kind of heat dissipation, right? So if you want something that is that has a band gap of about 5.5 eV, so it's a pretty good insulator, but has the thermal conductivity of copper. Look no further than HBN. The only way to do better is diamond, right? And you know, diamond's got its own problems, but we're also looking at diamond a little bit with collaborators, right? But still, that van der Waals interface between whatever and HBN is still tricky, right? And so I think it's hard to control that. One way to control that is to apply strain, possibly, or actually like squish things together. Like if just squeezing the van der Waals interface will increase the heat transfer, right? But you know, that's something that we're still thinking about. And if you have some good ideas, please, let's talk.
Professor, anyone needs to eat?
Oh, I'm happy to take that. I'm jet lagged, right? So, oh, I see, okay. Because you know, for me, it's 10 a.m., right? So,
Yeah.
that's not much. That's not much.
All right, thank you so
Okay,
much.
thank you.